So a little bit of review. So sulfuric acid what is the formula without looking at your notes? So what does this tell you, the name? It tells you that the base, so the base is sulfur. We get that from this portion. And this portion tells us that this is going to be the 8 version of it. So 8 referring to the oxyanion. So that means it's going to be SO with some number of oxygen. But how many oxygens does so these two together tells us we are dealing with sulfate. How many oxygen does sulfate have? A nice way to remember this is all the 8s, all the common ones, are in this form, XO3, with the exception of 2, SO4 and PO4. So this is the exception, and so it has a charge of number of oxygens of 4. What is the charge on it? Well, we know the 4 oxygens gives us a total charge of 8. Sulfur is not a halogen, so the number of valence electrons are going to all be removed and given to the oxygen. Sulfur is in group 6. So that means it is going to lose all 6 of its valence electrons. 6 plus negative 8 gives us a 2 negative charge. And acid tells us that there's going to be a hydrogen ion attached to this. So we're going to get a hydrogen ion that's going to interact with SO4 2 negative. And when we crisscross, the 2 is going to come attach itself here. And so the correct formula, and the one we don't have to put down, so the correct formula for sulfuric acid is H2SO4. Sulfurous acid, same thing. So this tells us this is going to form an ite oxyion. And this tells us our base. So we know that 8 version of sulfate, so sulfate is this. We've already figured that out. And when we go to an ite, we remove an oxygen and keep the charge. And the acid tells us that there's going to be an H plus ion to it. So in other words, this is H plus with an SO3 2 negative. We do our crisscross, and this is the formula for that. So again, without looking at your notes, what is nitric acid? What is the formula for nitric acid? So, yes, nitrate. So remember, our common 8 are all O3 except for sulfate and phosphate. Chromate is also a 4, but we can ignore it because it's very uncommonly used. In this class, sulfate and phosphate are very, very commonly used, and a lot of the other 8s, such as carbonate, is commonly used. So these are going to be our 2 main exceptions to the O3. So the ick tells us it's an 8. Nitrogen. So this is nitrogen-based oxyion. So we have nitrate. So this is going to be in the form of NO3. What is the charge? Well, we have 3 oxygens. Their net charge is going to be -6. And how did it get -6 charge? Because it's going to strip the valence shell from the nitrogen. Nitrogen is in group 5, so it has a +5 charge. These add together to give us a net charge of negative. So it's NO3 negative. The acid tells us H+. This is a 1-to-1 ratio, so the correct formula is HNO3. What about hydrochloric acid? What is the formula for that? The hydro tells us this is binary. Very simple. We're going to have an H+, and we're going to have a single element over here. The base is chlorine, so Cl negative. 1-to-1 ratio, so the formula is HCl. And something like potassium hydroxide is very easy. We have potassium, and you most definitely need to have OH negative memorized for hydroxide. Very seldomly will I give you the formula for a base. I usually will give you the name potassium hydroxide, calcium hydroxide, because those chemicals are most often referred to as name as they are so commonly used in a lab. So this turns into KOH. I said calcium. Calcium hydroxide. Calcium, Ca2+, hydroxide OH. So when we crisscross, the 2 is going to distribute on the OH. Can y'all see this all right? Makes sense? By the way, why is it important? Why do you think it's important to know this? To know how to go from a name to a formula? Because the reason we do nomenclature and why it's very important to learn in chemistry is because there's a lot of chemicals. You're not going to be able to memorize the formula for every single chemical. Instead, you just memorize the rules. And from the rules, you can go to an equation. If you remember, these are the 2 common exceptions. Everything else is O3. A lot of times you'll walk into a closet and you'll see the word sulfuric acid labeled on a bottle. And a lot of times you have to think about Alright, I need to mix an acid with its base to neutralize it and do something. A lot of time, you'll actually have to work out the chemistry in your head. Which acid is better? All you have is the word. Maybe you need something that has 4 oxygens, or maybe it needs to be 3 oxygens on it to counteract it, or else you get an explosive gas reaction. Maybe you're reading some instructions that have sulfuric acid as an instruction, and you were lazy and you put on 2 bottles only the formulas. H2SO4 and H2SO3. You didn't write the name with the formula on the bottles. You need to be able to go from the formula back into a name and grab the right ones. As if you get the wrong chemical, it can do vastly different results. So let's continue from yesterday. So we did percent composition. Basically, you just look at molar masses. I don't like converting everything to grams. I just know that in this formula, I have 2 sodium. So the total molar mass, and I use grams per mole. I don't convert to grams. So look at the periodic table, multiply it by 2. That's how many molar mass of sodium for that chemical. Then you do sulfur, then you do oxygen, multiply oxygen by 3, because that's the formula on the periodic table. Then add them together and you get the total mass. And then to find the percentage of sodium by mass, you take the mass of the sodium and you divide it by the total mass. So this is 36.486% sodium by mass. Sulfur is a little over a quarter by mass. And oxygen is 38% by mass. I will say this, one little tidbit. I have went to college and have worked in higher levels of math. You have most likely been taught that you should multiply formulas by 100 to get percent. Is that what y'all do? So, when doing a percentage, like for example in this, it says to get the percent mass, you take the total, divide by the molarity, or take the mass of the element, divide by the mass of the compound, and multiply by 100 to get the percentage. Were y'all taught that? Because my math teacher would be screaming at this in college. You multiply by 100%. I will say that this 0.5 is 50%. I will call this 50% and I will call this 50%. To me, there is no differences in these two numbers. This is 50%, this is 50%. This is 0.5, that is 0.5. Mathematically, they are equivalent. This percent sign tells you that what this is. It's like going from inches to feet. If I do 12 inches versus 1 foot, it's the same thing. These are equivalent. I don't mix them up, and I don't like the fact that it tells you to multiply by 100 because these two things are identical. If I ask you what is 50% of 2, what you're doing is multiplying it by 0.5. This was more aimed to my 6th period class that kept on getting confused because I will constantly, when I'm writing this down, I will occasionally leave it as 0.75 and say 75% while I'm writing. Or I'll occasionally write and say, well, this is 0.75. I hope it doesn't confuse you too much, as these two things are just two ways of saying the same thing. 0.75 and 75% is the exact same thing. Just as saying 12 inches versus 1 foot. I just hope that doesn't really confuse y'all too much. To me, I will use it interchangeably because it's the same number. So, empirical formula. Empirical formula is the lowest whole number ratio of the elements in a compound. The subscript cannot be a fraction. So, the empirical formula for caffeine, which the picture on the bottom right is of caffeine, is C8N4O2H10. That's the formula for caffeine. The empirical formula, we notice all of them can be divided by 2. So you divide everything by 2. The empirical formula is C4N2OH5. Note, in most chemicals, the empirical formula and the actual formula are not the same chemical. For example, a very common example is hydrogen peroxide, H2O2. This is a compound. It is hydrogen peroxide. If we reduce it to its empirical formula, OH, this doesn't exist as a compound, it only exists as the ion hydroxide. Or I guess you could rearrange it and do it like that. This is the empirical formula for this. Oftentimes, whenever we're trying to study new chemicals, how do y'all think we make new drugs and stuff? How do you think we know what the formula of things are? Do you think we just take a microscope and zoom in and look at all the atoms and count them? In extreme cases, we can do X-ray diffraction. If it's a crystal that's highly ordered, and we can basically get the arrangement of atoms and do some sort of very advanced calculations. But mostly what we do is we take the chemical and we put it in something known as a mass spectrometer. Spectrometer. And what this does is we take a sample, we put it into this device, and it's going to turn it into a plasma and break it all apart. It's going to superheat it to an extreme temperature, and then it's going to shoot it. It's going to turn it into ions. That's what plasma is a collection of ions. Plasma is where it's so hot the electrons doesn't take, and then we send these ions through a magnet. Due to complicated physics, as it goes through a magnet, it's going to deflect, and how much it deflects depends on mass. So we can basically put a scale on a wall, measure how much it deflects, and say that this is 500 AMUs, this is 20 AMU mark, and we can count how many particles hit and do some statistics, and we'll wind up and say that it's 20%, or we'll wind up and say it's about 11% hydrogen, and about 89% oxygen. We'll then get the empirical formula for this. We'll see that the ratio is 2 hydrogens for every oxygen. By mass, it's 89% oxygen, 11% hydrogen. We can convert, and then we can ask ourselves, what formulas have the same empirical formula as H2O? The most common one would be water. So that's actually how, when we create new chemicals, that is the most number one way we check what formula or what chemical we've created, is to actually decompose it by mass and figure out what the composition is. So what would be the empirical formula for glucose? So glucose is C6H12O6. What is it? CH2O. So the empirical formula for glucose, so the formula unit is C6H12O6. We see the least, or the greatest, the greatest common denominator of these is 6. So we divide everything by 6. So 6 divided by 6 is 1. 12 divided by 6 is 2. 6 divided by 6 is 1. And we can omit. And we get omit the 1s and we get this. Do y'all know what chemical this is? This is formaldehyde. Looks like carbonated water. You do not want to try sweetening your tea with formaldehyde. It's very bitter. Very unpleasant to drink. Do you know how I know this? Do you know how I know this is very unpleasant? Because I've accidentally tasted it. What's formaldehyde in? So, let me look up. This is actually a perfect example. My Coke Zero has an artificial sweetener called aspartame, or however you say it. Let me look up the chemical formula for that, because I'm actually interested. Yeah, sometimes. Its formula is C14H18N2O5. I don't know how we get from this to this. All I know is that after a few months of sitting in hot conditions, such as your car, this chemical will break down into formaldehyde. And I've gotten, when I was driving my truck, I reached in and grabbed one of my Coke Zeros and got an extremely bitter taste. And I wondered, like, what's the shelf life of a Coke Zero? And so I looked it up and found that in high temperatures, this chemical breaks down into formaldehyde. I'm like, I should quit drinking this immediately. It's toxic. It probably didn't have enough concentration to really hurt me, but it's very bitter. So CH2O. By the way, to answer your question, do you know what the formula is for carbonated water? There is no formula for it. It's a mixture. CO2 is just dissolved in the water. It's not chemically bonded to it. You could maybe, I'm not entirely sure if this is right. You could maybe write it as H2O dot CO2. The dot, in which case this would be called carbon dioxide. Oh, so it would be hydrate. And you would write it as CO2 dot H2O because you put the hydrates at the end of it. But I'm not for sure that that's right. So it wouldn't be carbonate. No. I guess then it would be. Maybe. Hold on. Let me look at that. Carbonate is CO3. Maybe I could be wrong. It could react because it makes carbonic acid. Carbonic. I'm actually you are right. So let's work that out too. My screen on. So what is carbonic acid? So when you have CO2, I was wrong. So when you do have CO2 dissolved in water, it does react with the water and form ions and form an acid. So the ite tells us that it makes 8. So this is carbonate. And that's a CO3. Again, -6. So -2 times 3 is -6. This will lose all of its ions. That's a 4. This gives it a net charge of -2. And then the H plus over here. So this reacts. The 2 is going to distribute onto the H2. And CO3 here. So water, if you treat it as an acid and a base, water breaks apart into its ions. And then we're going to, so this is more advanced. Aqueous ions. Aqueous. Then we're going to react it with CO2, which is a gas. And what does that get? That would get, somehow we get H2CO3. So 1 oxygen here, 2 hydrogen there. Yeah, that's the formula. That's balanced too. So that's what happens. We'll learn later on. I told y'all something kind of wrong and kind of true at the same time. You can treat ionic properties whenever they mix in water. If you mix salt in the water, what's going on? So salt is NaCl. When it enters water, it's constantly breaking apart into ions, and they're floating around in the water. And they're constantly recombining back into salt. The reason why is water is slightly polar. And so this really positive side and this really negative side, water will occasionally pull them apart, but it's very brief, and they instantly slime back into each other. But they disassociate in water enough that allows chemical reactions to go on.
So that's why whenever you
this is the
salt water, it doesn't just like turn into pure sodium and chlorine.
Yes. I forget the exact reasoning how you should think about this. Because you don't ever get sodium. This doesn't behave as sodium by itself. Because remember, the properties of sodium is because it has 1 valence electron. Here, this ion of sodium does not have any. It's full. It's not going to react with anything unless it reacts with another ion. Kinda. But water can be also thought of as constantly breaking apart and reassembling itself. As one of the, so we have water with hydrogen. What happens is this hydrogen will kind of get farther away, and this one will get super close, and what will end up is occasionally we can treat this as an OH ion, and this is being a H plus ion. But then very quickly it'll bounce back and be true water. It's for mostly properties. By the way, we're going to learn how to do this eventually. So, I guess it's not truly dissolved. I don't know. It's really weird thinking about it in that way. I would have to do some more research to say anything for certain.
I'm just curious about how.
Because I want to say that not all of it, the whole thing obviously doesn't turn into carbonic acid. And I wonder how much percent of it is just CO2 dissolved and how much of it is carbonic acid.
I know that it eventually would go flat with carbonation, so I would assume it would be bonded too tightly if it can just go
yes.
flat and open.
That's the reasoning. That's the same reasoning I have, is that it can't be that stable. Because if you have pure carbonic acid, I'm assuming it maybe decomposes naturally. I know some chemicals can are unstable and break apart and decompose, like hydrogen peroxide. Do y'all know that hydrogen peroxide is mildly unstable? If we had a pure bottle of just H2O2, so it's 100% this. Very quickly, what you'll end up happening is you'll have something like H2O2 that's 80% and H2O 20%. It will quickly decompose to where you have there's some ratio. There's some ratio of where it's somewhat more stable. This is unstable to have this concentration. And what happens is light that shines on the bottle or shines and hits this molecule gives an electron enough energy to break off, and then you're going to end up with either hydrogen or oxygen coming off, and we get H2O. This is the reason why, what bottles is hydrogen peroxide stored in?
It's dark.
Dark brown. Have you ever seen any in a clear bottle?
No.
Because light comes in and breaks it apart.
Oh. I knew it was a mixture. I knew it wasn't pure hydrogen peroxide.
Yeah. But it's interesting that you can't really make 100% that will stay. And you can in a lab, but again, light is very sensitive. So there are three types of empirical calculation: mole ratio, grams, and percent. Mole ratio is probably the most useful. Grams, well, they're all three extremely useful. So to calculate the empirical formula for mole ratio, this is best learned by example. So I have these PowerPoints on Google Classroom also. So let's do this. Let's suppose we have 0.5 moles. I'm just going to make something up. Sodium. 1.25 moles of carbon and 1.33 moles of oxygen. What you want to do is get all three of these numbers into a whole number. So what is the lowest common multiple of 0.5, 125, and 133? Well, so this is a hard example. I would just, to make it easier, you should choose the lowest one. But we could also do not just the lowest one. We can just choose any multiple. So if we multiply all these by 100, that's 50 moles of Na. 125 moles of, and let's make this 1.3 of carbon, and 130 moles of oxygen. Let's go to the reverse now. What is the greatest common denominator of these? Well, they're all divisible by 5, right? So we can all divide them by 5. So that's 10 moles of that. 25 moles of this. And 26 moles of this. This is the greatest. This is the least we can reduce this by. So our formula would be 10 sodium, 25 carbon, and 26 oxygen. We cannot reduce these numbers by any more amount. Okay, it says in the formula, another way you could do this is to divide by 0.5 on all of them. Let's try that. So we have 0.5, we have 1.25, and 1.3. If we divide everything by 0.5, see if that works. That'd be 1. So 0.5 divided by 0.5 is 1. 1.25 divided by 0.5 is 2.5. And 1.3 divided by 0.5 is 2.6. So we're going to have a 1 to 2.5 to 2.6 ratio. So what is the only thing that the greatest number we can get to where we have no more decimal is multiplying all these by 10, which gives us a ratio of 10 to 25 to 26. So it says here, to calculate the empirical formula for mole ratios, divide each mole quantity by the smallest mole quantity. Assign ratios as subscripts. If any ratio are not even, for example, 0.5, 1.25, 1.3, multiplying by them all by the lowest common multiple to achieve a whole numbers, then place these numbers as subscripts. So let's do another example and one that's more easier. Let's suppose we have 2 moles of carbon and 6 moles of hydrogen. What would be the empirical formula for this? So it's going to be a 1 to 3 ratio. So basically CH3. So for the carbon we have 2, and we have hydrogen, which is 6. We can divide both of these by 2. I really don't like how they describe doing this. You just keep manipulating these numbers until you get whole numbers. I will say one exception. If while doing this, you get the ratio 1.99 and 3. If we were to round this, if we were to get the correct one, or if we don't round, we would see that we need. So let's say this is calcium. Or let me do this opposite. Let's say that we get 1.99 calcium. I did it again. So we get 3 for calcium, and we get. Trying to think. Yeah, calcium and aluminum. We get 1.3. Give me a minute. We get 3 for calcium and 1.99 for aluminum. If we were to find the least common one, we'd see that this is 300 and 199. So we would expect their formula to be calcium 300, aluminum 199. Don't do this. Your rounding mistake, if you get something that is like very close to something, go ahead and round this to 2. So that it's Ca3Al2. This is the point I'm trying to make, is you're going to very often get a lot of 9s. I've seen 1.97, 1.94. Again, where these errors come from is how precise your periodic table is and how many digits you use. Or how precise the formula gives you. Maybe they actually should have measured 1.99 moles of carbon. And their scale is off or something. So if it's super close to an integer, go ahead and round it. Or maybe they meant to do 1/3, so that'd be an infinite number of 0.3 or 3 carried. And they stopped it and told you 1.3 or 1.33. Here, there's no way you're going to work it out and get a whole number. In fact, going back to my original example that I was working on, I would have perhaps maybe assumed that this and this were almost equal, that these two should have been the same ratio. They're approximately 25. Maybe I went too overboard, in which case I can divide this again by 5, and the ratio should have been into C5O5. It depends on how close your formula is, or how much error is in your numbers. For the most part, I'm not going to do anything tricky like that. So if you're given grams, you're going to convert into moles and then do the molar analysis. Basically what this says. Convert all the grams into moles. You do this by dividing grams by molar mass. And then divide each mole quantity. So basically 2 to the 4 is the exact same previous steps. So let's show you this example. So suppose I had 13.5 grams of calcium and 4.05 grams of carbon and 16.2 grams of oxygen. So we went to the lab, we had some chemical, and we're trying to figure out what it was. So what I did was burn it, which released, or I did something that removed all the oxygen. I reacted it with something, and all the oxygen was knocked off. And I measured this new mass, taking into effect with how much mass I added by putting an acid to it, and realized 16.2 grams is missing. So I know it has 16.2 grams of oxygen. Then I do some other experiment and figure out that it has 13.5 grams of calcium and that it has 4.05 grams of carbon. Somehow I've figured out its percentage of the elements. Well, again, this one doesn't tell us as precise as our periodic table does. The molar mass of calcium is about 40.08 grams per mole. Grams is going to cancel and the moles go flip. And we see this is 0.337 moles of calcium. 4.05 grams, and they choose the value 12.011 grams per mole for carbon. This is going to end up being 0.337 mole of carbon. 16.02. They don't include the 4. And I also recommend you probably round these numbers already to 3 digits. So, we take the lowest number and divide it across all of them. So divide each one, so 0.337 divided by 0.337, it's 1. So 1 mole of carbon, or calcium. 0.337 divided by 0.337 is equal to 1 mole of carbon. And 1.01 divided by 0.337 is equal to 2.99703.264. We can round this to 3 digits. That is equal to 3. 3 moles of oxygen. So our ratio is 1 calcium to 1 carbon to 3 oxygen. What would be the name of this? So this is the empirical formula. Yes. So this is the empirical formula. It looks like it's calcium carbonate. But remember, this is the empirical formula. We don't know if it's truly calcium carbonate or not. We do know, however, that most ionic formulas, so I will write this, most ionic formulas, formula units, are the empirical formula, are equal to the empirical formula, or are the same as its empirical formula.
I have a question about the hydrogen peroxide.
Yes.
So you said it's sensitive to light. Like, is it super sensitive about breaking down, or is it a longer time?
How sensitive is hydrogen peroxide to light?
I was wondering if that would mean that for the bed.
It is sensitive to UV light, so sunlight.
Well, if I was in the bathroom cleaning a cut on my foot.
Oh, no.
Like if I turn the light
If you accidentally leave it out overnight, you'll probably lose a percentage.
But so it wouldn't clean me any better if I could keep the lights on.
No.
That's what I was wondering.
Yeah.
Like,
So if you leave it outside for a few hours, so it's UV light, it definitely breaks down. It is UV sensitive, so not by sunlight. By only sunlight, not by the light inside your house. 240 nanometer light is where it starts breaking it down. Here's a fun experiment you can do. Measure its concentration at every day. There's ways you can figure out a way to measure its concentration. Put it in a clear bottle, and every now and then it's going to take a few drops and measure its concentration.
Mr. West.
See you.